So we last class we were discussing, we defined generating function, moment generating function, and these are all some tools which we use to compute expectation, variance, or these are all some tools which are like later we will define something called characteristic function. These are all some very useful tools. Okay. So we defined so something. Okay. In the last class, I proved something like this. For example, e of x. If x is integer value, we will in this class we will work with. From the beginning we will work with integer value function, integer valued random variable. Then if you have integer valued random variable, not integer valued, non-negative integer valued random variable, then we prove the following: n equal to 1 to infinity p of x greater than or equal to n. We proved this in the last class. Okay. For example, we computed the mean of the geometric distribution by doing some calculation, by differentiating the power series and all that. But we can directly do that. If x is geometric, with some p, okay, then we know that this is just that 1 minus p, right? 1 minus p power n, right? N is equal to 1. Okay. So, and that the sum is immediately follows. It's 1 minus p by 1 minus 1 minus p equal to, so it's 1 minus p by. So this is the mean. You can calculate using this formula. This is an application of this formula for geometric distribution. If x follows geometric distribution, then p of x greater than or equal to n is 1 minus p power n. We proved it in the class. Using that, we can compute the mean. This is an example where this formula is applied. Okay. So we will be using, similarly, we will be using this moment generating function to compute some mean variance later, or to talk about some, when you have sum of two independent random variables like that. Okay. So if x is integer valued random variable, then we defined the moment generating function. We defined it like this: txt for t between 1 and minus 1. Okay. Maybe it's defined for a wider interval. Okay, but this is a priori for any given distribution, any given random variable. Random variable does not matter, only the distribution matters here. This is given by p of px, okay, which is actually equal to summation n equal to, it's 0 to infinity, okay, n fxn, the density. Okay. And it exists because it's this, not n, fxn t power n. I'm sorry, I have written the expression for expectation. Sorry, this is fxn t power n. Sorry. When you make a mistake, you should immediately point out. Okay, so this is the moment generating definition of moment generating function. Then we prove, first fact we proved is if pxt equal to pyt for two random variables or for two density functions, then the densities are same. Then the fx is equal to fy. Okay. If two random variables have the same moment generating function, then the densities are same. This is by equating the, you differentiate and equating and taking, by evaluating at 0, you will get that. We did it last time. Okay. Then we proved that if x and y are independent, okay, if x and y are independent, then the sum equal to, we proved this. These two we proved in the last class. Okay. So we want to make use of this. Okay. So to make use of this, we compute the moment generating function for some of the distribution, for binomial. The simplest one is binomial. Okay. Example 1. binomial distribution. Binomial f of k equal to, you know what is that? NCK. This is n. Binomial, I mean, if suppose x follows binomial with parameter n and p, n and p. So let's call it, let me call it B of this, okay? B of n and p. This means binomial n and p. Okay? F of k is equal to p power k 1 minus p power n minus k. This is for k less than or equal to n, greater than or equal to. So x follows that. Then Cxt, the sum is only, I mean, it's just a finite sum, n equal to 0 to n. So we have the same nk, p power k, 1 minus p power n minus k, then p power k. So you can take this t with this p power k, and this is just Tp plus 1 minus t power n. Okay. So we have computed the moment generating function for binomial. Okay. This is just direct. Okay. So as a corollary to this, you can see the corollary to this. If you have two binomial, I mean, actually this is true for n of them. By induction, this is true for n of them. x1, x2, up to xn. Then the xn of pxn of t, it's just the multiplication of all of pxn. Okay. If here, if x1, x2, xn are independent, you can, I mean, this generalizes to n of them by induction. Okay, that's clear. So if you have n random variables, okay, then the moment generating function of the sum of the random variables is just the product of the moment generating functions. Okay. So if we have xi, this follows binomial nip, okay, and xi's are independent, I equal to xi independent for I equal to 1 to n. Okay. Then x1 plus up to xn will follow binomial summation ni, I equal to 1 to n with p. I mean, the p should be same. It follows from this immediately, right? You just multiply it ni, you will get the sum on the top. The p will remain the same. Is it clear? I'm saying that if each xi follows binomial with parameter p, the probability p and 1 minus p, and the number is number of times the binomial, that is ni, then the sum will follow summation ni with the same p. It just, I mean, this is the phi xt. You multiply it, all of them. I mean, if only the ni varies, you multiply all of them, then it will sum in the top. So it is just summation ni p. So this, if you want to compute it, you have to, I mean, if you want to compute the density function, you have to do many things. It just follows immediately once you know once you compute the moment generating function. So this is an example of an application. Okay. We will have similar application here for the negative binomial distribution. So these two, suppose x follows negative binomial. How shall I write? I don't know. Negative binomial. Negative binomial has a parameter alpha and t. Okay. That is fx at n equal to 0, 1, 2. This is equal to minus alpha. I wrote what is the expression for this when I gave the example. Minus alpha n, okay. Then minus 1 power n, p power alpha, 1 minus p power n. Okay. This was the expression for negative binomial. Okay. How we got it? I mean, we can write it in a different form also, which I discussed in the last class. I mean, in that class, but we will use this. This will give a better expression. Okay. Okay. Then we want to compute the phi xt. Phi xt is nothing but summation n equal to 0 to infinity. Okay. So you should have this expression here, minus alpha n, then minus 1 n p power alpha, 1 minus p n, and then t power n. Okay. And then t power n there. Okay. This is the moment generating function. If you just write the definition, it is this. So now this is equal to, I have already told you this is 2, no? 1 by 1 plus t power alpha is equal to summation minus, I mean, n equal to 0 to infinity. This is a Taylor series, minus alpha n, okay, and then what is that, t power alpha. Okay. If you use that formula, you get this pp alpha by, so I club this 1 minus pn, tn, all those things, okay, so which will be 1 and minus 1 also, 1 minus t times 1 minus power alpha. Okay, I just use that formula, Taylor's formula, Taylor's series formula. So then I get this. Okay. So corollary to this, immediate corollary to this. Okay. If xi follows I equal to 1 up to n of them, xi follows negative binomial with alpha I and p. I mean, if you vary the p, also you can compute, but it's not, again, not a negative binomial expression, something else. You can compute it. Okay? You just have to multiply that. That's all. Okay? Then summation xi will follow negative binomial. It's again negative binomial. Summation alpha I with the same p. Okay? If you just multiply, the alpha I will add the power, and then you will have the same p. So you get this. Okay? Similarly, you can do it for Poisson. It's very easy to remember Poisson. Okay? It is just e power lambda is summation lambda power n factor. Okay? So it is just the nth term. So Poisson is the nth term is just lambda power n factorial. But you need to get 1. So you have to multiply by e power n. Okay? If you have e power lambda or something, if you have something else, it will be, these things will be strictly greater than 1. So yeah. It is, you don't need to, you shouldn't memorize. You should, but you should know this. This is, I mean, basic of basic calculus or function theory. Okay, so from that it follows immediately. So for Poisson, now you can compute. So if you, f follows this, f follows x follows Poisson lambda, then pxt is summation n equal to 0 to infinity e power minus lambda is here outside, and then you have t power n, then lambda power 1 by n factorial. Now this is e power minus lambda plus lambda t, that's all. Okay, e power lambda t minus lambda. That's all. You got it as a function. And similarly, we prove the same thing. If some x follows Poisson with lambda, y follows Poisson with mu, then x plus y will follow Poisson with lambda plus mu, which we have already proved by computing it directly. Okay, but it follows from this also. I don't want to write it. So which follows from this also. So n of them also, it's true for n of them also. The same idea will work. Okay. So these are all some application. We will prove something more. I mean, when you later, when you study stochastic process or something, there is something called stop time, but I'm not going to define those concepts, but that is involved here. This is example 4. You have n random variables. I mean, you have not n variables, you have countably many random variables. Okay? x1, x2, x3, it goes on like this. xi, I is, I mean, countably many random variables. They are called IID random variables. IID means independent. This board is not writing. Independent and identically distributed. They have the same distribution and they are all independent. That's all. Okay. That's all IID. Okay. So identically distributed, IID. Y means, I'm just assuming you have something. X and Y are independent. You will ask why X and Y are independent. They are all, I'm assuming I have this is an example. You have, is an example. Suppose you have why it exists, you are asking a fundamental question, then that's different. Now, what's your question? I am saying you have an example, you have some binomial, you have some normal distribution or something. Suppose you want suppose. You assume that you have now what is your question? You have a question now? Identical distribution, they all have the same distribution. X and Y can have same distribution, both can have binomial. No? Two random variables, of course, if you want to compare them, they should be defined on the same probability space, and they can have same distribution. Okay, they have the same distribution and they are independent, which is, I mean, finitely many, it's clear how to do it, I defined. For infinitely many also you can define it. If you just have to take the countable product and make sense of it and do it, since if there is a need, we will do it later. But here you assume that, I mean, okay, it can exist. Okay, I mean, given any density function, you can construct such random variables. It's possible, but I am not giving a proof now. But I have given for finitely many. Okay, just take the product space and do that. Okay, so here we are assuming they have identity. And n is another random variable. This is also a random variable, independent of all those things. I mean, this distribution has nothing to do with that. Okay, independent of all of xi. Okay. Then you define a new random variable, Sn equal to summation I equal to 1 to n s n equal to 1 to n Sn. I mean, the sum will also vary. So if you want, this is Sn of omega for any given omega. Any given omega, n of omega is a number. Okay, and here assume that x is also integer value. Okay, omega to integer value. I mean, 0 union. Yeah, I mean, that's because, I mean, it's convenient. We want to construct, we want to study the moment generating function. So that's why I'm assuming it's all integer value. Okay, so this is n equal to, so n omega is a number. So you can have this, but this sum will vary. The number of elements in the summons will vary. Okay, so you can have this xn. Okay, xn of omega. For each omega, you can define like this. Okay, that's what I'm calling there. Okay, it may be 1, it may be 0, it can be anything. Okay, so n is also a integer valued random variable. If you want, you write it. I said everything is integer value. Okay, value. Okay, random variable. Then Sn you define it like this. Then what is? Sorry, Xn. Good. Sorry. Yeah. There is no small s. Xn. Small Sn means sum up to n. And here, I mean, yeah, it is basically small. I mean, this is basically n, but here the n is also varying. That's all. Okay. Then phi Sn at t equal to phi of n at phi of x1 at t. Okay, it's just composition. It's not multiplication. Composition of function. Okay, I will prove this. Okay. Statement is clear. Phi Sn. Sn is a random variable. The moment generating function of this random variable Sn is n is also a random variable. Is also random. These are all functions. This is just a composition of these two functions. That's all. Okay. So proof. Okay. So what is, we just directly compute phi Sn. Why? x1, yeah. Because you can have anything you want. Nothing about x1. You can have any xi. Because small, whatever you said, small Sn is just sum of, exactly. You just count the number of, yeah. You can have anything you want. Xn or anything you want. Okay. So now phi Sn at t equal to, the proof is very simple. N equal to 0 to infinity, then you have t power n, and you have so what is it? You have to write the probability, I think. Probability of Sn equal to n t power n, right? Okay. This is definition. Okay, the density. Okay. Now this is equal to summation n equal to 0 to infinity. Okay, I keep the t power n here. Sn equal to n. Okay. But then this n can vary here. Okay. So this is probability of this idea we have used several times. Okay, I'm just repeating. Sn equal to some m. Okay, and Sm equal to n. Okay. Fine. I mean, and this is union of this. 1 to infinity. Correct, no? Yeah, I'm also thinking whether I think it's fine. Okay. I mean, Sn equal to n. Here is something you just sum over all. You just take the disjoint union over all possibilities over n. N is a random variable taking values in natural numbers, union 0. Okay. So it just takes all values from 0 to infinity. Okay, it takes all values. Okay, so for any two values, the set is disjoint. If it takes 0, it's not. If it takes 1, it's not going to take 2. So it is a disjoint union of m equal to 0 to infinity. Okay. So this is fine. Xn equal to n. Sn equal to n. This is comma. If you want, you write it and. Okay, let me write it in a big expression. Okay. Probability of, okay, Sn, union of all these things, n m equal to 1 to infinity. You have Sn equal to n, n, and n equal to m. This is the intersection if you want. Correct, no? Yeah, n is a random variable, it takes the value m. It has to take one of this value. Okay. Above what? Yeah, now this yeah, sorry, n equal to n, sorry. N equal to m and Sm equal to, sorry. Now this is okay. Earlier I wrote something else. Is that true? No, I think I wrote, earlier now only I wrote the wrong thing, I believe. N equal to m and Sm equal to n. Yeah, that's what I wrote earlier also. This time I wrote it like this, but earlier I wrote it like, anyway, it's okay. Doesn't matter. Okay. This is the right expression. Okay. N takes the value m and it varies over m equal to 0 to infinity and Sm equal to n. This is fine. Okay. Now this is equal to n equal to 0 to infinity, t power n, summation n m equal to 0 to infinity. Okay. Then this is just Sm. I mean, we can take the yeah. So now wait. Sn equal to n equal to 0 to infinity, n equal to m. Yeah. I interchange it. Okay, for the time being. So there is a probability here. I forgot. P of this. Okay, P of this. No, there is a probability. Oh, there is a probability I have written outside. Sorry. Yeah, I have written probability outside. Sorry. Yeah. So let me just sum it. Okay, this is just the probability of. Okay, they are independent. Okay, so Sm equal to n, and probability of n equal to m. Okay. Now Sm. Okay. Now this is equal to summation n equal to 0 to infinity. I interchange n and m. Okay. Summation n m equal to 0 to infinity. Summation n equal to 0 to infinity. Okay. I interchange the m and m, and this is going to be, you have a t power n here, and then probability of Sm equal to n t power n, and then there is no n here in this, so this is just probability of n equal to n. This is okay. I have taken the sum outside, interchange the sum. Okay, they are all okay. So I interchange the sum, and then I mean you should justify. You can, okay, and then you get this. Okay. Okay. This is fine. So now this is equal to, I write the same thing, m equal to 0 to infinity. Okay. Then summation, I mean, then I have the probability, which is just Fn of m. I write it as Fn of m. Okay. Then that is going to be, okay, so summation, I mean, that is just phi. Here there is no, I mean, this is just, I mean, there is, this is just phi Sm of E, right? So which is same as, let me write it in another, m equal to 0 to infinity Fn of m, okay, which is just phi x1 of t power m, right? Because they are sum of independent random variables because of that. So instead of t, you have this here. So this is phi of n of phi of x1 of t. Yeah. So that's why I have taken x1. You can take anything you want. Okay. This water is good. I don't know. Huh? You don't think so? If you haven't said, I would have taken. I think they feel it recently. It's okay. If I die because of this. Okay. This is okay, no? It's very simple. Not the water. Yeah. This is okay. These are all very simple things. Okay. So this is an application of, I mean, it's very, actually, it will be very difficult. So now you have got a nice expression. Sorry, this should be n. Is that what you are saying? Yeah, there is a problem. I don't. Yeah, this is my problem. I make this mistake. I don't keep a notes and copy or something. So I think about something and I may write something else. And it's better because you should be alert. Okay, you should get confused and ask me, and we will remember that. Okay? If you make a mistake, we'll remember that. Okay. So this is okay. This is what you want to do. This is composition, not product, right? So this, of course, once you know the phi and once you know phi x1, you can just compose it and get it. I mean, so, okay, this is very nice formula. Okay, this is the derivation of that. So now we want to start something new, which is called moments of distribution, moments of random variable. Okay. Which is just expectation is the first moment, and the nth moment is just x power n. Okay, so x is a random variable. Then we say nth moment exists. For x if e mod x power n is less than infinity. That's all. Okay? If the nth power of the random variable, it has finite expectation, nth power of the modulus of the random variable, if it has finite expectation, then we say this. Okay, and the definition of nth moment is x is just e x power n. Okay? So the first remark is remark number 1 is if e mod x nth moment exists, okay, then e of x m is less than infinity for all m less than or equal to n. Okay. This should be fairly clear because x of omega, we proved that if x is less than or equal to y for two random variables, then the expectation of x is less than of expectation of y. So if my x is, you just have to know that mod x is less than or equal to, let me write, minimum minimum of 1 mod x power m, okay, is less than or equal to minimum of 1 mod x power n. Okay, is right? No, if x is greater than 1, then x power m for m is less than n, x power m is less than x power n. If it is less than 1, they are less than 1. Okay, now this has finite expectation. I mean, this is a new random variable. If you have x power n is one random variable, one is one random variable. This is a new random variable. So minimum of 2 random variable is again a random variable. If that has finite expectation, this has finite expectation. You can easily see, right? Minimum of 2 random variable. That has, if x and y has finite, I mean here one is constant. If x and y are have finite expectation, 2 random variable having finite expectation. Minimum also has a finite expectation. We are going to sum. We are going to take the minimum. Okay. Maximum also will have finite expectation. Yeah, okay. So it's not a problem. I mean, if one of them, so yeah, maximum will also have finite expectation. So this is fine. Okay. Maximum will also finite expectation. No? Yeah. Huh? Yeah. So this works. Okay. When it is less than 1, the inequality will be other way, but we are taking 1 here, which is constant, which is the, because the density function sums to 1, it's because of that, because it's probability measure. Usually with integration, this will not work, but here it works. Okay. So because of that, it follows. Number 1. Number 2 is if x, y are such that, this is the board which is not ready. X, y are such that E of, I don't know, E of x power n less than infinity or E of y power n less than infinity, then sum also it's true. X, of course, always, nothing else. Okay. Okay. X, y are random variables, then each time I don't want to write. Okay. So this is true. So this is true even, I mean, if n is not an integer, you can make sense of these things and it will work. But that involves some concave function of calculus. So I don't want to go into that. You can directly prove it. So the thing is, you want to consider x plus y power n, okay, which is less than or equal to mod x plus mod y, mod x plus mod y power n, of course. So which is equal to summation n equal to 0 to n. See, k equal to 0 to n. We see k mod x power k mod y power n minus k. Okay. So x and y are real valued, mod x and mod y are real valued. So either one of them, given any omega, one of them will be greater than the other one. I mean, one of them will be greater than the other one. X is greater than y or y is greater than x. So this is less than or equal to k equal to 0 to n. So whatever happens, nk plus, you can just write it as mod x power n plus mod y power n. I mean, either x is greater than y or y is greater than x. If x is then that will be dominated by that. If y is greater, that will be dominated by that. So you can replace x by the y and you will get this. If the other case, this will dominate that. So it follows. Okay? And you don't have any k here. You only have this. And this sum is 2 power n, right? 2 power n. So this is equal to 2 power n mod x power n plus mod y power n. So x plus y power n is, this inequality is true if n is real valued. I mean, need not be integer, but for that you have to work with do some calculus, concavity or something. Okay? Let's not do that. So for our purpose, this is enough. Okay. So from that it follows. That's all. No, we need. This is less than that. So if you take E of this, then E of this is linear. So because of that, it follows. So both are finite. So that is also fine. Okay. What is the next one? Oh, it actually is on it. Okay, let's go back to our moment generating function. Actually, I didn't take in the notes. I haven't taken the notes. Okay. So we want to compute our expectation and variance from the moment generating function. Okay. Moment generating function. So you have, okay. Usually variance is this. Expectation, we know what is expectation. Variance of any x is E of x squared. E of, I mean, it's the expectation of this. Or this is what is called centralized moment. Okay. So x is a random variable. And let us say mu equal to ex. Okay. This is the number, mu equal to ex. Okay. Then E of x minus mu, okay, power n. Okay. This is what is called centralized nth moment. Okay. And centralized second moment is what is called variance. Okay. You must be knowing. Variance of x equal to E of x minus mu square. And the square root of this is called standard deviation. Let's not say all that. Okay. So you must be knowing these things in your higher secondary. Okay. So this is variance of this. And you can compute this. This is equal to E of x square minus E of mu, I mean, 2 mu ex times, what is it? 2 mu ex minus mu square, right? This is also mu plus mu square, which is equal to ex square. I mean, ex equal to mu. So this is just ex square minus, if you want mu square, or you write ex square. We just expanded, you get this, okay? Just we just, you know this formula, I'm sure, okay? Variance of x is ex square minus ex whole square. That's all I want to say. Okay. So, and you know that expectation is the expected value. It is just what you can expect. It is just you average it out. It's an average, weighted average. Variance is weighted. It's a kind of weighted average of that difference. So it is like how it is distributed around that expectation. Expectation is some sort of mean, and I mean it is mean, some sort of what you expect, and it is just how it distributed. How so if expectation is 0, then it's a constant random variable taking the value mu, expected value, right? If variance of x equal to 0, that is E of x minus mu square equal to 0. Okay. If expectation of a positive random variable is 0, if you want, this is just summation f x minus mu square fx at x, right? If this is equal to 0, then it can have value only here, only for x equal to mu. This implies x equal to mu, almost whatever I defined as almost sure. Okay. A probability of x equal to mu is 1. Okay. This is what I called as x is equal to mu almost sure, almost surely. Okay. So variance of x is 0, then it is equal to mu almost surely. Okay. So is there anything else to say? If there is anything else to say, I will say it later. Okay. So let us discuss this moment generating function. So x is a random variable, and phi xt is the moment generating function. Xt is the generating function. Okay. Then we can get the expectation, and I mean we can get any nth moment. So, but we are interested in the we are interested in the mean and variance expectation, first moment and the second centralized moment. Okay. So for that we write the formula. Pxt is this summation n equal to 0 to infinity t power n fx at n. So if you differentiate once, p prime xt, this is a power series. Here there is a point I want to say. I forgot, sorry. See, Usually this is defined for t is between 1 and -1, right? That is how we defined it. But suppose if it is defined for something bigger, some t naught greater than this, then we can differentiate at 1. We want to differentiate it at 1. That is possible if we can differentiate, if it's defined for our binomial, negative binomial, it is defined for something more. For negative binomial, see what is the formula? Do I have the formula here? Yeah, it's here. So for negative binomial, pxt equal to p alpha, if I remember correctly, then what is this? 1 minus t into 1 minus p, right? This is the pxt for negative binomial distribution. Okay, and this is valid for, this is valid not just t between -1 to 1. This is valid for t into 1 minus p less than 1, which is like t less than or equal to 1 by 1 minus p greater than or equal to 1 by 1 minus p minus 1. This, whatever that power series, if you look at that power series, which is a Taylor series, which is valid for all these t. That Taylor series, we got this for negative binomial by using a Taylor series. That Taylor series is valid for all these t. Okay? And 1 minus p is less than 1. So this will be greater than, this will be less than -1, this will be greater than 1. So it is something bigger than 1. The interval is something bigger than 1. For Poisson, it is everywhere. Okay? For Poisson, it is just, we use the e power t formula, so which works everywhere. Okay? Binomial, we don't have to worry, it is a finite sum. Okay? Which is everywhere, which is convergent everywhere. So when we have this expression, okay, maybe I'll write it again. When pxt, I mean, for the x is a random variable, or the distribution of x is such that we have that expression, we have that power series expression valid for a bigger t. Okay? That is equal to summation fx n t power n infinity for t less than or equal to some 1 plus epsilon. So let's say t naught minus t naught, where t naught is strictly greater than 1. Then we can differentiate it 1. Okay? Usually this kind of series, power series, may not be differentiable, that we will only demand continuity at the end point, okay? Not differentiability. So if it is slightly greater than t naught, then we can talk about differentiability. Okay? That's why I am using this. Okay? Then it's clear. You can differentiate it. Phi of t, p prime t is going to be summation n equal to 1 to infinity, then n times fx n e power n, right? Similarly, phi x double prime t, you can go on doing it. Okay? You can n time differentiate. You can differentiate any number of times. N equal to 2 to infinity, n into n minus 1, sorry, n minus 1. N minus 1 fx n into t power n minus 2. Okay. So this thing says, if you substitute t equal to 1, this says that expectation of x is nothing but phi x, phi prime x at 1. Right? If you substitute t equal to 1, this is just this sum. This sum is nothing but expectation of x, right? Expectation of x is summation n fx n, right? Okay. So similarly, this is n into n minus 1, which is the, when we have used the formula. So expectation of x into x minus 1 is equal to phi x prime double derivative at 1. So we have got these two formulas from the moment generating function. So these things imply, from here you can get ex square minus ex whole square, that is equal to ex double prime 1, that will have a ex here, so you have to add it. Okay, but then that is just phi x prime 1. Okay, then ex square, this is phi x double prime, sorry, phi x prime 1 whole square. This one, here, phi x square, phi x, phi that's double prime, no? Phi x double prime. Yeah, I'm just including it here. I mean, it's just algebraic, no? So I just missed one step and then directly writing it. I mean, provided I write it correctly, which I think it's the case. So this is the formula. We got two formulas for computing the mean and variance. Okay. Maybe I should leave it as an exercise or something, or you can compute. Okay. Here we have done this. So if we have a negative Poisson distribution, example, negative binomial distribution, okay, then E of x, we just have to differentiate that formula. We have that formula. Where is it? I have erased it. Okay. Then phi xt is p power alpha 1 minus t into 1 minus t, right? Power alpha. Huh? It's above. Yeah, good. Okay. Okay, this is the formula. Okay. So phi prime, should I write all that? You can compute the variance and the expectation. Okay. Similarly, you can do it. Maybe I will do it for Poisson. Okay. Poisson. Suppose x follows Poisson lambda. Okay. Then phi xt, we computed it, which is just lambda t minus lambda, right? Lambda t minus lambda. So this implies phi x prime t, which is, okay, I have to substitute, right? So which we already computed the mean by direct computation, but it will follow from here also. Lambda into e power lambda t minus lambda. If you substitute t equal to 1, that will become 0. So this implies Ex equal to lambda. Okay. Similarly, if we have phi x double prime t, another lambda square will come, E lambda t minus lambda. Okay. This implies Ex square minus, okay, we just have to use that formula. So variance of x, if it follows Poisson, variance of x will be, if you substitute 1, you will get lambda square minus plus lambda, right? Plus lambda minus lambda square, which is lambda. So for Poisson, both mean and variance are lambda. Okay. You can do it for other examples. Okay. Okay. Okay, I will do something non-trivial today. So have you seen this Cauchy-Schwarz inequality? You know the proof of it. You know the proof of it, but general linear product, all of you. Remember the proof? Okay, I can prove it again. It's very easy. So the thing is, if we have a vector space, the point is this. So you have collection of all these things. I need a new notation. XV we have used. So L. If you have a probability space, some probability space, so the omega script A P is a probability space. Okay. Then LP of omega, we are only discussing with Ln of omega, okay, is all those random variables x from omega to R, such that Exn, this is less than, okay, or we just take it as 2. Okay. 2 is less than infinity. We can define it for LP, but this is for just L2, we can define it. Okay. So on this, we can define an inner product. So if x and y are in L2, I just write it as L2. then you define xy to be just E of xy, the product. Okay. I mean, here it's all real valued. You can consider complex valued if you want. Then it will be linear in the first variable, anti-linear in the second variable, and will satisfy all that. And the xx will be positive, and it will satisfy all these things. Okay. So this is, I mean, here it's just real value, so you need not worry about conjugate linearity. So this is an inner product. Okay. What is that? What is that? L2, I'm defining a space, vector space. This is a vector space, right? You can add two random variables. Still, it will be square interpretable because we have proved it. This is an inner product. Inner product will give something called norm. Norm will give something called a metric. You have done metric spaces. You got introduced. Okay. So inner product will give a norm. This is just an inner product. I'm not talking about anything else. This is just an inner product. Okay, you know the properties of inner product. No, it is linear in the first variable, anti-linear or again linear in the second variable. Then x should be positive. This is just ex square, which is positive. And when it is real, there's nothing more to do. Yeah. So you will give a norm. For that, you have to verify the triangle inequality. For that, you need the Cauchy-Schwarz inequality. Okay. This, yeah. So maybe proposition or whatever. I mean, the Cauchy-Schwarz, what we have is the following: E x y square. Xy are two random variables. I mean, we have two random variables defined on omega, xy and L2. Then this is less than or equal to Ex square times Ey square. Which is same as saying, which is equivalent to saying x, y. I mean, which is same as saying xy square. I mean, if you square it, you don't, I mean, this is not complex valued. Otherwise, you have to put a mod and other thing. If it is complex valued, you have to put a mod. I mean, square is need not be positive, you know, in the complex case. So you have to put it here. It's okay. This is square is less than or equal to xx, which is we usually call as norm x square, norm y. So this inner product will define a norm on that. That norm will give you a metric or whatever you want. Okay. Then you can talk about convergence and all those things. Okay. Shall I prove Cauchy-Schwarz inequality? It's not needed. Anyone? No. No, you don't need. Okay. Okay. So I think we'll stop here today. Okay. Short class.